Good afternoon and welcome to the session on ETC 779. We are into lecture number 22 and in this class we are going to cover the remaining portion of risk analysis. In the previous class I defined what is meant by risk and then we tried to learn few basic things as far as probability is concerned. We discussed about the addition of probability values. We discussed about the multiplication of probability values and then we finally did try to discuss some aspects of expected value. So, in this particular class we are going to follow the contents shown on the slide. We are going to discuss further the expected value. We are going to discuss two cases, one in which the cash flows are supposed to be independent. In another case, we are going to discuss the expected value corresponding to the case in which the cash flows are dependent. We will discuss about variances, we will discuss about coefficient of variation, and we will also be discussing about investment risk profile, acceptable investment diagram, and then finally we will be seeing some of the auxiliary criterias that are helpful for evaluation of alternatives. So, this is the plan for today's lecture. More or less we will be covering all these aspects. If not, then we will have to continue in next classes. Now, we will straight away move into expected value part. Last class we defined expected value as the weighted average of all values where weights being the probabilities. So, if you try to write down in terms of certain mathematical expression, you can write it like expected value of x is nothing but sum of the multiplication of ith value of variable and its corresponding probability. So, it is nothing but summation I is equal to 1 to n xi multiplied by probability of xi. So, this is the simple mathematical expression we are going to use for calculating expected value. Now, I can calculate the expected value for demand, I can calculate the expected value of return, I can calculate the expected value of salvage value, I can calculate the expected value of interest rates. So, why we are trying to use expected values here is that now we have got number of possible values and we have also assumed the corresponding probability values of their occurrence. If you try to distinguish this particular scenario with the earlier classes, you will easily find the difference. In all our previous analysis, we had assumed that the values whichever is taken for our problem are bound to be occurring. They are certain to occur, they are sure to occur. But here what we are doing is we are having different values and we are also having the associated probability of occurrence. So, when these values as well as the probability values are given, we can find out the expected value, which is nothing but the weighted average. Last class we tried to solve one or two examples. We will do some more examples in this particular class also. So, this particular exercise was given to you in the previous lecture, in which there are two options of investment. In one investment, you can earn 100% return, but there is a probability of only 0.3. You can earn 15% return in case normal situation prevails and the probability of normal situation is 0.4. In case there is a recession, you can lose some money also. Your return is going to be minus 70% and the probability of facing a recession situation is 0.3. So, for this particular investment option, we had seen how to calculate the expected value. Now there is other investment option also given to us, which says if the situation is good, that is it's a boom time, you are going to get a return of 20%. If the situation is normal, you are going to get 15% rate of interest, a rate of return, and if the situation is that of recession, you are going to get 10%. Now I will apply the formula that we discussed in previous slides and then try to calculate the expected value. Now the illustration of this expected value computation is given in this particular slide. You can find that expected value for the second alternative comes out to be 15%. How it has been calculated? It has been calculated by summing up the product of rate of return and the corresponding probability values. So for example, you can see very clearly that you are getting a sum of 20 multiplied by 0.3, because there is a 30% chance that you can earn a rate of return of 20%. There is a 0.4 probability that you are going to earn 15%, and finally there is a 0.3 probability that you are going to earn 10%. So I have just calculated the weighted average and I have found that the expected value of return as far as the second alternative goes is 15%. Now incidentally, if you try to calculate the expected value of the first alternative, you will find that you are getting the same expected value, 15% only. The problem has been designed to make them equal. We will show why we have designed this problem like this after some time. So in this case also, for calculating the expected value, you have to multiply 100 with 0.3, add it to 15% into 0.4, and then finally add it to minus 70 into 0.3. So incidentally, you will find that the expected value for this particular alternative is also 15%. Now which one to choose among these two, we will see after some time. Now I will take another example of computing the expected value. In this example, I am taking that the 3 end of year returns and the corresponding probability values. For example, year 1, I am expecting that I can get 1500 rupees with a probability value of 0.25. In year 1 itself, the chances that I am going to earn rupees 3000, its probability is 0.5. And finally, in the same year, year 1, the chances that I am going to earn rupees 4000 is 0.25. Similarly, for year 2 and year 3 also, I have assumed certain returns and their associated probability values. At time t is equal to 0, I have assumed that I have to invest rupees 6000. Discount rate is assumed to be 10%. The same problem I have tried to show it in the cash flow diagram form, which is shown here in this particular slide. What you see in this particular slide is at time t is equal to 0, you have to invest rupees 6000, and at the end of year 1, there are 3 cash flow values and corresponding probability values. For example, year 1 you can see 1500 probability is 0.25, 3000 probability is 0.5, and 4000 probability is 0.25. Similarly, for year 2, you can see that for getting a return of 1500, probability value is 0.5. For getting a return of 3000, probability value is 0.25. And for getting a return of 4000, I have a probability value of 0.25. Similarly, these three values of cash flow as well as the associated probability values are given for end of year 3 also. Now you can notice the difference between this particular cash flow diagram and the earlier ones. In the earlier cash flow diagrams, whatever we had done till now, we were having single value. And we were assuming that whatever is our estimated value is going to occur in reality also. That was our assumption. But in real life, it doesn't work out that way. Here what we are assuming that a cash flow at some point of time may have different values. Now, not only I have assumed those different values, I have estimated those different values, I have also worked out the chances of their occurrence. Now, still we are into very simplistic model. There could be situation in which we can have infinite possibilities of cash flows, different cash flows. So, what you find here is we are dealing with discrete distribution. There could be a scenario in which you have to deal with continuous distribution. So, if you just try to see what is the difference between these two, I will just like to show you one diagram and then it will be more clear. Say for example, at the end of year 1, you have a chance to get 1500 rupees, you have a chance to get 3000 rupees and you have a chance to get 4000 rupees. The associated probability values corresponding to these cash flows or these returns I am also trying to plot. For example, this is 0.25. So, if this is 0.25, for this it is 0.5. And finally, for this it is 0.25. So, what you find that I am having 3-point estimate. I am saying that there is a 0.25 or 25% chances that 1500 would be the return at the end of year 1. There is a 50% chance that I am going to get 3000 return, and there is again a 25% chance that I am going to get 4000 rupees as return at the end of year 1. This is again a simplistic approach. In real life situation, the values may not be out of these three alone. There could be a distribution like this. There could be a distribution like this, in which you can have infinite number of return possibilities with different probability values. For example, getting the return of this probability could be this, like this, like this, like this, like this. There could be n number of possibilities. So, depending on how you think a particular variable is going to behave, you can assume a suitable distribution. It could be exponential distribution, it could be logarithmic distribution, it could be normal distribution. So, basically this also is very, very important. Your estimate of a particular variable's behavior is going to influence your decision. In this particular example, I have taken that there are only 3 possibilities, and that's why I have assumed the 3 associated probability values only. That means my basic assumption here is that the cash flow is going to be either 1500 or 3000 or 4000 at the end of year 1. But if I continue to work like this, I will take an average value or expected value, and that you know how to calculate. For end of year 1, I will get the expected value like this: 1500 multiplied by 0.25 plus 3000 multiplied by 0.5 plus 4000 multiplied by 0.25. You will get a value of 2875. So that will be my expected value of return at the end of year 1. I can calculate the expected values of returns at the end of year 2 and at the end of year 3 in a similar manner. Now, once I have got the expected values with me at different point of time, I can calculate the net present value. Now, one more assumption I am making here. What is that? I am assuming that my return at the end of year 1 and my return at the end of year 2 are not at all related. Please note this point. There are two assumptions that we are adopting here. First one, that variable values is having a 3-point estimate or a distribution which is getting fitted into these 3 points. And second assumption is that the cash flow at the end of year 1 and the cash flow at the end of year 2, they are not at all related. That means the cash flows at different years are independent. That is very, very important. Right now we are dealing with the situation in which cash flows at different point of time are not at all related. In real life situation, it may not be that so. Sometimes you will find that if you are getting a good return at the end of year 1, you are likely to get slightly good return also in year 2, or it could be even bad, but somehow you will find that they are related. So we will see how to calculate expected values under such conditions in which they are related, they are correlated. That means they are not at all independent. But concentrating on this particular problem, once I have calculated the expected values at different year, I can calculate the net present value like this. Net present value, as you can very clearly see, is given by minus 6000 plus 1500 into 0.25 plus 3000 into 0.5 plus 4000 into 0.25 divided by 1.10. I have tried to use the formula. If you try to use the interest rate factors, it is still possible. You have to multiply this with P given F for an interest rate of 10% for year 1, for a period 1. Similarly, in second expression, you can see I have divided it by 1.1 raised to power 2, which is nothing but P given F at an interest rate of 10% for a period n is equal to 2. And finally, in the third expression, I have divided it by 1.10 raised to power 3, which is equivalent to P given F for an interest rate of 10% for a period 3. Now, if you calculate it this way, you will find that net present value is coming to be 1027.58. So, this is how we incorporate the expected values into our calculations. Now, if you would have worked out the net present value without assuming these different returns at different point of time, we would have got certain different values of net present value. We have been doing it that way in our beginning classes. But here the problem has changed. Now I have different possibilities of returns at different point of time. And this is how we calculate the net present value. Now we will see one situation in which return of one year is dependent on the return of other year. That means the cash flows are dependent. For example, if you look at this particular problem, what you see here is that there is an investment option in which at time t is equal to 0, you have to invest 200,000. It could be dollar, it could be rupees, whatever it is. The idea is at time t is equal to 0, that means just now you are going to invest $200,000 or rupees, and you are likely to get a return of 80,000 in year 1, and the chances that you will get this particular return is 0.3. Similarly, the chances that you will get a return of 110,000 in year 1 is 0.4. And similarly, the chance that you are going to get a return of 150,000 in year 1 is 0.3. So, year 1 we have got 3 values, and we also know the associated probabilities. It is 80,000, probability is 0.3, 110,000, probability is 0.4, 150,000, probability is 0.3. Now, we will consider the return at the end of year 2. What you find here is that the return at the end of year 2 is dependent on the return of year 1. So, you can see very clearly in this decision tree diagram, from the point 3 node, that means from the first node top, you have got 3 more nodes emerging. So, for year 2 you can find that you have a possibility of making 40,000, 100,000 and 150,000, and the associated probability values are 0.2, 0.6 and 0.2. Now, why I am calling the 2 cash flows are dependent? Because this year 2 return will be possible only when the return at the end of year 1 would have been 80,000. In that sense, they are dependent. Similarly, for second node, you have 3 nodes emerging, and the corresponding rate of corresponding returns are 130,000, 150,000 and 160,000, and the associated probabilities are 0.3, 0.4 and 0.3. And finally, from the last node, 3 more nodes are emerging, and the corresponding returns are 160,000, 200,000 and 240,000. The associated probability values are 0.1, 0.8 and again 0.1. Now, the question before us is how to calculate the net present value. So, there could be 2 methods of solving such type of problems. One, we will do it like this. This is method 1. Method 1, I will calculate net present value like minus 200,000. There is a mistake there. It should read it as minus 200,000. It is wrongly written. 20,000 is wrongly written. Minus 200,000 plus 0.3 multiplied by 80,000 divided by 1.12. I will write it down, it will be more clear to you. The net present value would be minus 200,000 plus 0.3 into 80,000 divided by 1.12 plus 0.2 into 40,000 plus 0.6 into 100,000 plus 0.2 into 150,000 divided by 1.12 raised to power 2. So, this is from first node. Likewise, you will have for second node, which will be plus 0.4 multiplied by 110,000 divided by 1.12 plus 0.3 into 130,000 plus 0.4 into 150,000 plus 0.3 into 160,000 divided by 1.12 raised to power 2. And finally, for the last node, it would be plus 0.3 into 150,000 divided by 1.12 plus 0.1 into 160,000 plus 0.8 into 200,000 plus 0.1 into 240,000 divided by 1.12 raised to power 2. And this you get it as 19,036.98. So, this is the value of net present worth that we are getting. This is as far as method 1 is concerned. In situations in which we are assuming that cash flows at different point of time are dependent on each other. Now, the same problem I will do it in a slightly different manner. If you try to remember the previous lecture, we had defined multiplication of probabilities. Whenever we had a sentence like what is the probability of this and this, we used to take the product of the two probabilities. So, the same concept of joint probability we will be using as method 2. So, if you just see this particular slide, I am interested in calculating my probability values like this. What is the probability that in year 1 I am receiving a return of 80,000 and a return of 40,000 in year 2? This is my problem statement. I am taking the first path, 80,000 in year 1 and 40,000 in year 2. So, see the term and. So, probability that I will get 80,000 in year 1 is 0.3 and probability that I am getting a return of 40,000 in year 2 is 0.2. So, the joint probability would be 0.3 multiplied by 0.2, which would be 0.06. You can understand it from this particular diagram. I have got one path like this, another path like this, and from here I have got a total of 3 paths. This is 80,000. This is 40,000. probability is 0.3, probability is 0.2, probability is 0.6 and probability is 0.2. This is 100,000, this is 150,000. I am showing you one portion of the total decision tree. Now what I am interested is the probability that in year 1 I am going to get 80,000 and in year 2 I am going to get 40,000. That means I am interested in going through this path. So my probability value is going to be 0.3 multiplied by 0.2. Likewise, I have calculated the joint probability corresponding to all the 9 paths. There are 9 paths in the decision tree, and for each one of them I have calculated the joint probability. For example, for path 1 it would be 0.3 into 0.2, so it is going to be 0.06. For path 2 it is going to be 0.3 into 0.6, 0.18. For path 3 again it is going to be 0.3 into 0.2, which is going to be 0.06. Likewise, the first column is giving you the joint probability values for all the 9 paths. Now what I am going to do is, forgetting about the probability, I am just going to take each path individually and I am trying to calculate the net present value. For example, I am interested in calculating the net present value for this path, path 1. Here I have minus 200,000. That is the investment I have to make, and that is why I am putting it as minus 200,000. So the net present value for this particular path is going to be minus 200,000 plus 80,000 divided by 1.12. Let's say 12% is the interest rate. In this example, assume that 12% is the interest rate, plus 40,000 divided by 1.12 square. This is nothing but minus 200,000 plus 80,000 P given F for an interest rate of 12% for a year 1 plus 40,000 P given F 12% for a period 2. So both expressions are same. Either you use your interest factors, or straight away you can use the formulas. So you will find that the net present value for this particular path is going to be, I will write it with different ink, is going to be minus 96683.67. You can cross check it. So this is the net present value of first path, for which the joint probability has been calculated to be 0.06. Now in the similar manner, I am going to take all the 9 paths separately and going to calculate the net present value. This has been already calculated and it is shown on your slide. If you look at method 2, the second column gives you the present worth or the net present value for different paths. Altogether there are 9 paths. So I have calculated the present worth for all the paths separately, besides calculating the joint probability for each of the paths. you can notice that for first 3 paths I am getting a negative present value. From 4th path onward I am getting a positive value. Now, in order to calculate the expected value of NPW or NPV, I am going to multiply the joint probability with present worth of different paths. So, the first rather second row you will find that you are getting a product of minus 5801, which is nothing but multiplication of first column and second column. So, in order to get the weighted outcome, you have to multiply the first column with the second column. This will be more clear if you look at this particular example which we are trying to solve. In this, we had a net present worth of minus 96,683.67 and the probability value is 0.06. So, this and this I am going to multiply and the result would be minus 5,801.02. So, this is the weighted outcome from path 1. This exercise I am going to do it for all the 9 paths and I am going to add all of them. So, that means column 3 I am going to take the sum of it and you will find that you are getting the same value which is coming to be 19,036.98. So, this is method 2 in which we are using the concept of joint probability. Now, whichever method suits you, whichever method you feel you are okay, you can use that to calculate the net present value. Now, we will move to second part of this discussion. We will be discussing about measures of variation. The main objective behind finding the variation is to know which alternative has got more risk associated with it. Whenever we talk of variations or variance, it's in some way gives us a measure of risk. Suppose that somebody is giving an estimate and his estimate has got more likelihood of getting changed. We don't have that much confidence in that particular estimator. What we are interested in is that particular proposal in which we have more confidence, we can impose more confidence. So, in order to instill confidence in the decision maker, you need to report values which are not varying that much. And this variation in the estimates is measured by a statistical term called variance, sigma square. And if you try to calculate the sigma value, that is known as standard deviation. Then there is another term which is quite often used to measure the variation. It's known as coefficient of variation, CV. So, these 3 particular terms are used more often for reporting the variance or rather reporting the risk involved with the particular alternative. Now, what I will do is I will just introduce you to the expression that we need to use for calculating the variance. Before that, if you try to look at these two proposals, in proposal 1 or proposal A, if the demand is low, it is going to give you 900. That means in case of low demand, you can expect that 900 is going to be your sale. In case of average demand, you can expect that your sale is going to be 1000. And in case of high demand, you expect that your sale is going to be 1100. In proposal B, you find that sale corresponding to low demand is 400, corresponding to average demand it is 1000, and corresponding to high demand it is 1600. Now the probability for low demand situation, for average demand situation and high demand situation is also given to you. For example, for low demand situation, probability is 0.2. For average demand situation, the probability is 0.6, and for the high demand situation, probability is 0.2. Now suppose we have to choose between the two. Suppose you are the manager and your two subordinates have given you estimate like this. Which one you would like to opt? That means out of the two proposals submitted by two different individuals, which one will instill more confidence in you? So in order to have confidence, or in order to find out the measure of confidence in different proposals, we try to calculate the variance. Variance associated with each of the proposals. And that is calculated by, I will give you the expression for that. Variance is calculated by summation I is equal to 1 to n xi minus expected value of x whole square multiplied by probability of xi. This is basically giving you the dispersion or deviation from your mean values, from your expected value. How far away you are there from the mean value. So this particular term measures that. So what you find that if you apply this particular formula, you can calculate the expected value of demand in proposal A. You can see it has been calculated as 900 multiplied by 0.2 plus 1000 multiplied by 0.6 plus 1100 multiplied by 0.2, which is equal to 1000. So you understand how to calculate expected value. We have solved a number of examples, so there is no problem. Now in order to calculate the variance, you need to know your expected value. Now expected value in both the cases, it happens to be 1000. Now we would like to calculate the variance in demand for proposal A as well as for proposal B. So the variance of demand in proposal A is given by 0.2, which is nothing but the probability, multiplied by 900 minus 1000. 900 is the value of demand and 1000 is the expected value, square of it, plus 0.6 into 1000 minus 1000. 1000 is the demand and 1000 is again the expected value. So this is going to be 0, plus 0.2 into 1100 minus 1000 whole square of it. So we are getting the variance for proposal A as 4000. Now if you try to see the proposal B, you will find the variance in it is coming to be quite large, 1,44,000, 144,000. Now this particular thing will help you in coming to a judgment. You find that in proposal A we have a variance of 4000, whereas in proposal B you have a variance of 144,000. So that means estimator in A, he is quite confident of his estimates because the variance of his proposal is quite low, whereas the estimator of proposal B is not confident of his values. That is why he has given you a large range, right from 400 to 1600, whereas the range if you see for proposal A, it is from 900 to 1100 only. So estimator for proposal A is quite confident, whereas estimator for proposal B is not that confident. So this is how we try to make decisions based on the variance. So this is also known as minimization of variance principle, in which we try to select that proposal which has got low variance in it. Now this particular illustration I will try to continue with the problem which we did today for calculating the expected value. Now this particular problem had two alternatives. In alternative 1, you had a investment in which you could make 100% return, and then you also had a possibility of making a negative return, minus 70%. The first problem which we did today. Whereas in second option, the range is very low. In normal time, you were earning 15%. In boom time, you were earning some value, 20%, and in recession, you were earning only 10%. So corresponding to both the proposals, you can just calculate the variance. You can just